We're now going to have a look at the types of simple machines. Now, there are in fact 6 different types of simple machines, and we're going to start by looking at each one of them in turn. So let's begin by looking at the inclined plane. So what is an inclined plane? Well, an inclined plane is a ramp that is used to lift a heavy object to a certain height by the application of a small effort. So if we look at the diagram here, you can see an example of this. This is the inclined plane, this is the ramp. And you can see that the force which is used to move this weight up the ramp is 300 newtons, and the weight is 1,500 newtons. So we can see here that by using a small force, we're able to apply a small effort in order to move this rather heavy load up the ramp to the top of the ramp. So in fact, the inclined plane is actually operating as a force multiplier, and it can be called a force multiplier simple machine, because what you're doing is you're applying a small force in order to move a larger force, and so you're multiplying the force. Now, this is rather interesting because if we look at the force required to lift that particular box from the ground into the truck, if we use the relationship that the potential energy is equal to mg times h, then we can see that the amount of energy required to lift it to that position would be mg, which would be 1,000 newtons, multiplied by h. So let's assume, as in this example, the height is 1 meter. Therefore, the gravitational potential energy would be equal to 1,500 newtons multiplied by 1, which is going to give me a gravitational potential energy of 1,500 joules, or newtons per meter. Now, that would be the amount of energy required if I was to lift it from the ground right into the back of the truck. But here you can see that I'm only applying a force of 300 newtons, not 1,500 newtons, to push this box up the inclined plane into the truck. So the inclined plane is actually multiplying the force. It's acting as a force multiplier. Now, the mechanical advantage, as you know, is equal to the load divided by the effort. And we can say that the load is in fact mg, because that's the weight of the actual object. So it's going to be mass times g. And so we can say that the mechanical advantage is the load divided by the effort, in this case mg over effort. Now, if the surface of the ramp is actually smooth, or let's say it's frictionless, then what we can say is that the mechanical advantage is going to be equal to mg divided by mg sine theta. Now, in order to understand why we have mg sine theta, you need to have a knowledge and understanding of the free body diagram associated with this particular setup here. So if the surface is smooth, in other words, if it is frictionless, then there won't be any other forces acting on the actual box. So the force required to move the box upwards along the inclined plane will be mg sine theta, where let's assume the ramp makes an angle of theta with the horizontal. Then mathematically we can show that the force going up the actual inclined plane will have to be greater than mg sine theta in order to move this box up that plane. So that assumes that there is no friction, it's actually smooth. Now, the mathematics for this is quite easy to understand, and we'll cover it when we look at examples of simple machines which involve inclined planes. So in other words, we can simplify this mg over mg sine theta. And remember, mg sine theta is the effort force in order to move the box up the inclined plane. And so when we simplify this, we can see that the mechanical advantage now is going to be equal to 1 over sine theta. And remember, this only applies when the surface is frictionless, is smooth. Now, if the surface is rough, then we have to take into consideration frictional force as that box is moving up the inclined plane. It's going to be opposed by friction. So not only do we need to apply a effort, which is going to be equal to mg sine theta, in order to move the box up the plane, we also have to overcome the frictional force. And the frictional force is equal to the coefficient of friction, mu, times mg cos theta. And this particular expression is obtained from the free body diagram. And it would be based on the trigonometry and the geometry associated with this diagram. And again, we'll look at this in more detail when we look at some worked examples. So, in other words, for a rough surface, the mechanical advantage is equal to mg over mg sine theta plus mu mg cos theta. And we can simplify that by taking the mg's out and putting them outside a bracket, which has 1 over sine theta plus mu cos theta, where mu is the coefficient of friction. And so that then gives us an expression for the mechanical advantage being equal to 1 over sine theta plus mu cos theta. We're now going to have a look at wedges. And wedges are very important because these are both force multipliers and direction changer machines. So now let's have a look at the velocity ratio in terms of a wedge. Now the velocity ratio, VR, that's going to be equal to the ideal mechanical advantage. And that's going to be equal to the length divided by the thickness. So the length of the actual wedge divided by its thickness will give you the velocity ratio, which is also equal to the ideal mechanical advantage. Now we know that the percentage efficiency is going to be equal to the work output divided by the work input multiplied by 100%. And we can in fact write this as the load times the load distance over the effort multiplied by T. This was one of the ways that we derived work output over work input. You can represent it in this way. You can actually do the derivation if you like to see how this is actually equated to this. And so that's multiplied by 100% to give you the percentage efficiency. So let's have a look at an example. A 10 centimeter thick and 30 centimeter long wedge is used to pierce an object. What is the velocity ratio of the wedge? So let's have a look in terms of what we're given and go through the solution to this particular example. So we're given that T is actually the thickness, and we're given that L is equal to 30 centimeters. So what we're trying to do is to determine the velocity ratio. So the velocity ratio is equal to the length divided by the thickness. And so if we substitute what we have, we know that the length is equal to 30 centimeters, and we know that the thickness is 10 centimeters. Therefore, the velocity ratio is going to be equal to 3. Now, a screw is a thin cylinder or cone with a spiral ridge, and this is a ridge thread which runs around the inside or the outside of the screw. So here you can see the different types of spiral ridges. Some of them are in terms of their separation. This one has a larger separation compared to this one. In other words, we say the pitch is larger in this particular screw compared to this one. What is a screw used for? Well, a screw is used to hold objects together. It's also used to dig into the ground. It can be used to bore through rocks. As we've said, the distance between successive threads, this is called the pitch of the screw. And so the mechanical advantage, as we know, is equal to the load divided by the effort. And the velocity ratio is equal to the effort length divided by the load length. Now, in terms of the effort length, you can see probably by looking at the diagram here that the effort length is actually the circumference. If you turn the screw when it goes round, then that is in fact the circumference. And we know that the circumference, assuming that this is a circle, that the circumference is going to be equal to 2 pi r. So the length is in fact the circumference, and the load length, well, the load length is going to be the pitch, because as you can see, as the screw turns around, in other words, the effort is applied to the top of the screw, so that it goes round one circumference, 2 pi r, then you can see that the load length is actually going to be the distance from one of the threads to the next. In other words, it's going to be the pitch, because the screw will go down by that amount when you turn the screw. And then in terms of the load, well, what will happen is that the screw will turn as a result of that, and you will see that it will go into the material by one pitch, which is the distance between each of the threads. So we can say that the velocity ratio is equal to 2 pi r over p. And in fact, you could write it as pi times the diameter over p, because 2 times r is the same as the diameter. So d is the diameter of the head of the screw, and it's important to note that 2 pi r, the circumference, is going to be greater than the pitch. Therefore, the screw is a force multiplier machine. So let's have a look at a worked example involving the screw in terms of looking at force multipliers. A screw has a pitch of 0.1 centimeters, and the diameter of the head to which the turning effect sets is 50 centimeters. If the efficiency of the screw is 40%, what must be the force applied to lift a load of 25,000 newtons? So in this particular case, we're told that we have a screw, and the pitch, the length of the pitch, or the distance between the threads, is 0.1 centimeters. We're told the diameter of the head of the screw is given as 50 centimeters. Also, we're told the efficiency of the screw is 40%. And we're asked to determine the force that needs to be applied in order to lift a load of 25,000 newtons. So let's have a look at the solution to this. First of all, we're given that the pitch is 0.1 centimeters, and we're also given that the radius is in fact 25 centimeters, because we're told the diameter is in fact 50 centimeters. We're told that the load is 25,000 newtons. So let's have a look at the solution to this problem. Well, we know that the velocity ratio is equal to the effort length divided by the load length, and we can write that as 2 pi r over p, where 2 pi r just represents the circumference of the screw. If we substitute in what we know that 2 pi r will be equal to 2 pi multiplied by the radius, and the radius is 25 centimeters because we're told that the diameter of the head of the screw is 50 centimeters. And we're going to divide that by the pitch, and we're told the pitch is 0.1 centimeters. Therefore, the velocity ratio, if you do the mathematics, will be equal to 500 pi. Let's not work out the value of pi yet. We'll just keep it here as pi, and we'll work it out later on. Now, the efficiency is equal to the mechanical advantage divided by the velocity ratio. And remember, we've determined what the velocity ratio is. It's 500 pi. The value of the efficiency is given in the question as 40%. So we're just going to write that as not percentage efficiency, but just the efficiency. So we can say the efficiency is equal to the mechanical advantage divided by the velocity ratio. And let's put the efficiency as 0.4. So 0.4 is equal to the mechanical advantage, which we can write as the load divided by the effort, all divided by the velocity ratio. Now, if we rearrange this expression here in order to make E the effort, which is going to be the subject, then what we get is E is equal to the load divided by the efficiency multiplied by the velocity ratio. And if we substitute in what we know from the question, we know that L is 25,000 newtons, and we also know that the efficiency is 0.4, and we've calculated the velocity ratio to be 500 multiplied by pi. So let's do the mathematics in terms of the calculation for this. And if you do that, substitute these values into your calculator, you should get a value for the effort to be 39.8 newtons. So 39.8 newtons is in fact the force that needs to be applied to lift a load of 25,000 newtons. So now let's turn our attention to levers. And we have looked at levers in some respect in terms of some of the forces which have been applied when looking at machines. But now we're going to be a little bit more specific and look at it in a little bit more detail. So what exactly do we mean by the term a lever? Well, a lever is in fact a simple machine which consists of, and if you look in the diagram here, this will illustrate it very well. It consists of a long bar which is pivoted about a fulcrum. So if we look at this diagram here, this animation, you can see that we have the long bar represented by the arm of this particular nutcracker, and we can see that the fulcrum is represented as F here at this particular point. And so when we talk about levers, we're really talking about long bars which are pivoted about a fulcrum, which can be acted on by a force to move a load. So in other words, we can apply an effort at the two ends of the lever, and by applying an effort, we also then apply a load, and that load acts upon the actual nut in this particular case. And so this would represent a simple lever, just to explain or to illustrate the definition of a lever as illustrated in this sentence. So let's have a look at some of the key definition terms relating to levers. So the fulcrum, well, that is the point around which a lever turns. So if you look at this diagram again, you can see that this particular lever is actually trying to, when you apply the effort, is actually trying to turn in this somewhat clockwise manner. And you can see here that the other end of the lever, in terms of the effort, is also trying to move in a kind of an anti-clockwise manner. So you can see, if we were to draw the motion of these particular levers in terms of their circular motion, they would be actually moving around the fulcrum, which would be the point at the center of the motion of these levers, if we could imagine them actually moving in this circular motion clockwise and anti-clockwise. And so the lever is a bar that is free to turn about the fulcrum. So again, you can see, using this simple lever diagram, that these would represent the bars, which are the hands of the actual nutcracker, and they're free to move around the fulcrum. Obviously, they don't actually move around completely in a circle, but you can see that they have the motion to move in this circular motion if they could. Now, the term torque, given by this symbol here, this is the turning effect of the force. So in other words, we can measure the torque in terms of the turning effect, the ability for the levers to actually turn around the fulcrum. That would be given the term the torque. And the torque is actually very important in terms of what it relates to. It's actually the product between the force and the distance from the fulcrum, or the axis of rotation. So that's a very good point. We can actually talk about the fulcrum in terms of it being the axis of rotation of the hands of the lever as they try to rotate when we apply force to them. So the torque is in fact the product of the force being applied, in other words E, and the distance from the fulcrum. So it would be the distance from the end of this particular lever to the fulcrum. If we could draw a straight line from that end all the way along to the fulcrum and measure that, and if we know the effort, E, or the force being applied, the input force, if we multiply that force by the distance from the fulcrum where the force is being applied, then that would give us the value of the torque. So we could write that in terms of a word expression. We could write that as the torque is equal to the force multiplied by the distance. Now, if we look at this particular diagram, we can see that we have a lever here, which is balanced in the sense that the lever is in the horizontal position and it's not moving upwards or it's not moving downwards at either ends. So that means that it's balanced. In other words, the anti-clockwise torque is equal to the clockwise torque. So for example, if we look at this diagram here, assuming that this is a balanced beam, in other words, the lever is balanced, in other words, it's stationary, it's not moving down or up at either end, then remember what we said about the torque. The torque is going to be the force multiplied by the distance in terms of the distance from the fulcrum. So this is the fulcrum here at this point where we have this wedge. So if we have a force of m1 at this end and we multiply it by the distance from the fulcrum, which is a, that would be m1 times a. And if that is equal to the force at the other end, in this case m2, and we multiply it by the distance from the fulcrum, which is b, then we can say that m1 multiplied by a is equal to m2 multiplied by b, and when that occurs, we can say that the beam is balanced, or the lever is balanced. Now, obviously, in this diagram here on the right-hand side, you can see that the lever is not balanced, and the reason being that the force exerted by the elephant at this end, where we have the arrow, is greater than the force exerted at the other end, but also you can see that the distance of the force of the elephant exerted onto the lever, the distance of that point from the fulcrum is also larger than the distance of the mouse from the fulcrum. So as a result of that, you can see why in this case the torque would not be balanced, because the force times the distance here is greater than the force times the distance here. So this is an example of a lever which is unbalanced. We're now going to have a look at how you can classify levers. In other words, the different classes of levers. Now, in the diagram you can see that there are in fact three classes of levers. There is the first class lever, the second class lever, and the third class lever. Now, if you look at the diagrams very carefully, you can see that the classes of levers depends on the position of a number of things. It depends on the position of the pivot. It also depends on the position of the effort force and also the position of the load force. So, depending on the positions of the pivot, depending on the position of the effort force and the load force, we can then classify the levers. So you can see in the diagram that in the case of a first class lever, the position of the effort force and the load force are given as in this diagram here. So you can see the effort force is at one end of the lever and the load force is at the other end of the lever, and the pivot is positioned somewhere in the middle of that lever. And then when we move on to the second class lever, you can see that the pivot is located at one end of the lever, and at the other end of the lever we have the effort force, in this case acting upward in the upward direction as illustrated by the green arrow. And you can see that the load force, represented by the red arrow, is acting downwards somewhere in the middle of the lever. And then finally, with the third class lever, you can see that the pivot is at one end of the lever and the load force is acting downwards at the other end of the lever, as in the diagram here, illustrated by the red arrow, and the green effort force is acting upwards somewhere in the middle of the lever. So these diagrams give you an idea of the classification of levers based really just on the position of the pivot, the load, and the effort relative to each other. Now, in the previous part of this section on levers, you saw that the mechanical advantage could be either greater than, less than, or equal to 1. Now, this is important because if the mechanical advantage is greater than 1, then what we have is an example of a force multipliers, because you're effectively increasing the force by the application of the lever. Now, if the mechanical advantage is less than 1, then what we have is a speed multiplier. That means the speed is actually multiplying. And if the mechanical advantage is equal to 1, then the class lever is going to be a direction changer. And so in many ways, just by looking at the mechanical advantages in terms of the load over the effort, then we can determine whether it's a force multiplier, whether it's a speed multiplier, or whether it's a direction changer. And so we're going to explore some of these levers in a bit more detail and start looking at the other classification of levers, in other words, second class levers and third class levers. So we've just looked at the first class lever. Now let's have a look at the second class lever. So in the second class lever, the load is placed between the effort and the fulcrum. So here you can see a very simplistic diagram showing you that taking place. Here we have the position of the fulcrum, here we have the position of the load, which is between the effort and the fulcrum, and at the other end of that lever we have the effort. And you can see that sort of illustrated here in this simple animation. Here we have the fulcrum, here we have the load, and here we have the force, or the effort force. So this is an example of a second-class lever. And examples of second-class levers, they include wheelbarrows, nutcrackers, bottle openers, and the office punch that you use to punch holes in paper. Now over here we can look at the forces involved in the position of the fulcrum for some of these. So for example, in the case of the wheelbarrow, you can see the position of the fulcrum, which is here, just where the wheel is, and you can see that the load would be represented by this arrow here, representing the load, which is the force acting downwards, and you can see effort is represented by the symbol E, representing the force acting upwards on the handle of the wheelbarrow. And similarly, if you look at the office punch, you can see the application of the force for the effort acting on the hands of the hole puncher, so to speak, and you can see where that would apply in relation to the load. And also you can see where the position of the fulcrum is in relation to the load and the effort. And similarly with the nutcracker, again, the diagram shows you clearly where the effort force is in terms of the end of the handles on the nutcracker, and then it shows you the corresponding load being applied as well as the position of the fulcrum. So an example of a second-class lever is given as, in the examples we have here, as either a wheelbarrow, a nutcracker, a bottle opener, or an office punch. Now there is another class of lever, which is the third-class lever. And if you look at the diagram on the right-hand side, you can see a simple illustration of a third-class lever. Now, in this lever, you can see the position of the fulcrum relative to the position of the effort force and the load. And if you look carefully, you'll see that the fulcrum is situated in such a way that the distance of the effort force from that fulcrum is given as SE, and the distance of the load force from the fulcrum is given as SL. And so the distance of the effort force from the fulcrum is less than the distance of the load force from the fulcrum. In other words, the effort is between the fulcrum and the load. And here you can see the arrow indicating the effort load. So this is an example of a third-class lever. Now examples of third-class levers include, for example, fishing rods, cricket bats, and also chopsticks. So going back to the diagram, you can see that the effort arm, which is this arm here, is less than the load arm. And so if we were to use the velocity ratio expression, which is that the distance of the effort from the pivot divided by the distance of the load from the pivot, or in other words, the effort arm over the load arm, well, by the very fact that the effort arm is less than the load arm means effectively that the ratio, in terms of the velocity ratio, is going to be less than 1, because the value for SE is always going to be less than the value for SL. So that's always going to give you a value which in fact is less than 1. So what does that mean? Well, it means because the value is less than 1 for the velocity ratio, it means that the mechanical advantage is also less than 1. And so as a result of that, the third class lever is going to be a type of what we call a speed or a distance multiplier. So it's not going to be a force multiplier, but it will be a speed or a distance multiplier.